Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on October 26, 2025, about 8 days ago. This paper trains a compact recurrent reasoning agent with reinforcement learning to navigate dynamic mazes and hits 99% goal success while carrying the latent state between steps, speeds learning by reusing prior computation. The paper is titled HRM-Agent, Training a Recurrent Reasoning Model in Dynamic Environments Using Reinforcement Learning. And as we'll see later, the implications for model training are quite significant, because reusing computation across time makes planning both faster and more reliable. Alright, Figure 1 presents the maze navigation tasks used for training and analysis. Panel A depicts the classic 4 rooms layout with doors that toggle, where exactly one door stays closed and can switch with 5% probability each step, so the agent must replan paths. Panel B introduces the dynamic random maze, which mixes fixed walls, extra random walls, and 5 doors that open and close independently. Panel C illustrates a valid route when doors allow passage, generated with A* to guarantee at least one solvable path. Well, Figure 2 details how the agent turns recurrent reasoning into actions. The diagram shows high and low modules that iteratively update a shared latent Z, while a 2-layer DQN head reads the final state to output action values. The dashed loops mark within step recurrence, and the red paths indicate where gradients flow. The blue arrows at left show Z being carried from the previous environment step, with no gradients across steps. So, Figure 2 mapped the computation flow. Figure 3 reports whether that reasoning actually wins. Figure 3 shows goal success rising with training, plotted as the fraction of episodes solved versus training mini-batches. Both panels reach about 99% success, which validates reliable navigation. Solid curves represent carry Z, and dashed curves represent reset Z, and carry Z typically climbs faster, especially in the random maze where most runs hit high success earlier. So the previous figure showed rising success. Figure 4 tracks efficiency. Figure 4 plots mean episode length versus training, which drops from around 80 steps to about 10, matching the theoretical optimum once doors are considered. The left panel covers 4 rooms, and the right panel covers the random maze. Solid lines represent carry Z, and dashed lines represent reset Z, and the solid lines generally reach short episodes sooner, especially in the random maze where most runs converge faster. Alright, the previous figure tracked efficiency. Figure 6 analyzes how the recurrent latent state, a hidden memory that stores the plan, converges in the random maze. The left panel shows ZL reaching its final value in fewer recurrent steps when carry Z is used, especially after environment changes. The right panel shows the same pattern for ZH, which confirms faster and smoother convergence. These trends suggest that carrying state lets the agent reuse prior computation and adjust plans quickly. Okay, the previous figure analyzed latent convergence. Table 1 specifies the setup that produced those curves. The agent uses 121 observation tokens and 4 actions, with episodes capped at 80 steps. The hidden size is 64, and the recurrent inference runs up to 8 inner steps, with 2 cycles and 4 layers in both high and low modules. Training uses a deep Q network head with discount 0.95, epsilon from 1 to 0.15 over 300,000 steps, and a target network with delay 0.999. Wrapping up, 2 takeaways stand out. Carrying the latent state across environment steps lets the recurrent reasoning process reuse past computation, which speeds training and shortens paths, and pure reinforcement learning suffices to reach about 99% success in dynamic mazes. The broader implication is practical planning agents that adapt online in uncertain worlds. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.